Hello, this video tells you what you need to know for the linear dynamics topic for the AP Physics exam. And for this video, we're going to walk through all these scenarios you can see along the top. But for all these scenarios, you do the same thing. You draw a free body diagram, then you need to align the XY coordinates with the forces in the free body diagram, and then you need to figure out the equations for the net force, Newton's second law. And then when you figure out the net forces along the y-axis and along the x-axis, you can use these equations to determine any answer for any of these. The first scenario is pushing or pulling an object. And you see the free body diagram here. If the object's just sitting on the ground, it's affected by gravity, and there's the gravitational force, and the way you calculate that is mass times the gravitational constant, which is either 9.8 or 10, depending on how accurate you want to be. If the problem has numbers in it that are rounded to 10, you could probably just use 10. But if the numbers in the problem are more accurate than that, then you need to use 9.8, or the problem may tell you to use 10 or 9.8. Okay, so that's the gravitational force pulling the object down. Then there is the normal force, which is stopping the object from going through the earth, right? It's the floor pushing back and saying, object, you can't keep falling. And normal in this context just means perpendicular. Okay, but when you set an object on a scale, what you're measuring is you're not measuring the gravitational force, you're measuring the normal force, how much the floor is pushing up against the object. Now somebody could be pulling or pushing the object, and this is called the applied force. And you may think that if a person was pushing this object, you would draw the arrow so that it's pointing towards the object, but that is not correct. In a free body diagram, you always draw the arrow pointing outward in the direction of the force. And the final force is frictional force, which is in the opposite direction of the applied force. And it's calculated using what's called the coefficient of friction, this Greek letter mu. And for instance, ice has a very low mu, or some rough surface like a wooden floor has a high mu. And you multiply this mu times the normal force, and you get the frictional force. Now this frictional force has a maximum, so if you push hard enough, you can overcome it. The next step we need to do is align the x-axis and the y-axis to our free body diagram. And what you want to do is you want to align the positive x in the direction you think the object is going to move. Now that we have that, we can make our equations. The net force in the y direction is the normal force, positive, minus the gravitational force, which is in the negative direction. And that equals ma, but because the object's not accelerating in the y direction, we can set this equal to 0. The net force along the x-axis is the applied force in the positive direction and the frictional force in the negative direction. And you don't know whether it's accelerating, so we just leave it as ma. These are our equations, and you can answer any question. Now, I want to mention that the mass is measured in kilograms, and acceleration is meters per second squared. So that means force, which equals ma, is the units are kilograms times meters per second squared, and this thing is called a Newton with a capital N. Now I have here a problem, and I encourage you to come back and work through these problems, or you can stop the video now and work through the problems, but come back and look at the problem. It's about Amy pushing a dresser. Okay, we'll go to the next scenario. This is pulling a block at an angle, so you're kind of lifting it and pulling it at the same time, like with a strap or something. And the only difference between this and the previous scenario is the applied force is at an angle, and so you have to do what's called project. You have to project the applied force on the x-axis and the y-axis. And the way you do this is the problem will give you an angle, theta, usually. And whatever axis that angle is coming off of, that's the adjacent axis, okay? And in this case, the adjacent axis is the x-axis. And you calculate the applied force along the x-axis, along the adjacent axis, by multiplying the applied force times cosine of theta. So cosine is adjacent. And then to get the applied force along the other axis, in this case the y-axis, you use the applied force times sine theta. So for sine theta is the other axis. And so that's what you need to remember. Cosine for adjacent, sine for the other axis. Okay, now what you're doing when you're pulling this a little bit upward, you're kind of lifting it. And just as if you would imagine you were some object were on a scale and you're measuring how much it weighs, but then you lift it a little bit, the weight goes down on the scale. The same thing is here. Because the person's pulling and lifting it a little bit, the normal force gets less. And so you're kind of lifting it and the normal force reduces. And as a result, because you're lifting it a little bit, the frictional force, because friction is mu times the normal force, and the frictional force gets a little bit less by lifting it. So we can look at we see this in our equations. The net force on the y direction is the normal force plus the applied force in the y direction. That's positive minus the gravitational force, which doesn't change because the gravitational force is what it is, whatever the mass is, and that equals 0. So you can see why if you apply more lift, your normal force goes down. Along the x-axis, you have the applied force along the x minus the frictional force equals mass times acceleration. So those are our equations, and I encourage you to come back and look what happens when Amy is pulling at this dresser at an angle instead of pushing it. Okay, the next one. This scenario is a block on an incline. And in this case, what we need to do, the key thing, is to rotate the XY axis so that it aligns with the direction, the positive X goes in the direction that you're planning to push the block. And in this case, let's make the positive X on the right. And we have two little sub-scenarios here. One is where the block is just sitting there, and the other is where the block is being pushed. In both cases, forces are aligned with the x-axis or the y-axis, except for gravity. And so gravity is what we have to project onto the x and y-axis. What we're doing is rotating the x and y-axis. So we're rotating the x-axis off horizontal by theta to the incline. At the same time, when you do that, you're going to rotate the y-axis off downward, and it also rotates by theta. So the difference between the gravitational force and the y-axis is theta. That means that the y-axis is the adjacent axis. So the gravitational force in the y direction is the gravitational force times cosine, and the gravitational force sine is along the x-axis. Okay, so for these equations, we can do the forces along the y-axis. That's the normal force minus the gravitational force along the y-axis. And for the x-axis, when there's no applied force, it's just the frictional force in the positive direction, because the gravitational force is in the negative direction and the friction's just holding it up. Now, it may slide or it may be held. So the MA may be accelerating or it may be 0. And then when you do the applied force is going in the positive direction, and the gravitational force is still negative, but now the frictional force, which is always a bummer, is also going negative and making it harder for you to push the object up the incline. So those are the equations, and it'd be very helpful to go through these steps. If you're ever stuck, go through these steps and you can derive the equations yourself. Here we have a example problem which I encourage you to come back and look at. Okay, so here's the next scenario. And this is the train scenario. And this kind of scenario is what is known as a two-body problem, where there's a link between the two objects. And in this case, we have an engine that's linked to a caboose, let's say. And in these kind of problems, you're often going to be asked to calculate what the tension force is between the two objects. So the way to do this in all these two-body problems is to first do a free body diagram for the whole system. Okay, so this is it of the whole train, and we have the applied force plus the frictional force for each car, and then we have the tension force, which is both the force experienced by the engine pulling the caboose, and it's also the force experienced by the caboose being pulled. And the two tension forces equal, and they cancel out. So assuming the train's on flat terrain, then the equation is for the net force along the x-axis is the applied force minus the sum of the frictional forces, and that equals the sum of the masses times the acceleration. And you can use this to calculate the acceleration of the whole system. And so now the second step is to get the tension force. And to do this, you can either start from the front or you can start from the back. And if we do it from the front, the tension force equals the applied force minus all the force that is used up by the engine, by M1. And that includes the frictional force on M1 plus the amount of force required to make it accelerate, which is M1 times A. Or you can calculate the tension force from the back, and that is the tension force equals the whatever it takes to move M2, and so that's the frictional force on M2 plus what it takes to accelerate at M2 times A. So you can do it either way, and it will depend on the problem. You can decide to do it one way or the other, but they will give you the same answer. So this is the train scenario, and I encourage you to come back and look at this example. Now we're going to go to the next example, which is the sliding block scenario. And this is also a two-body problem, and the two bodies are the cart and the block. The cart is like the engine, and the block is like the caboose. And when the cart accelerates or decelerates, we want to know whether or not the block will slide. In these problems, you're usually going to be able to, they'll give you the acceleration of the cart, and that could either be speeding up or slowing down. And so in this picture, we have the acceleration vector going to the right. And this could mean, and I'm going to ask you to use your imagination here, this could mean that the cart is going to the right, its velocity is to the right, and it's speeding up. And so you can imagine that if the cart starts speeding up, there is a potential for the block to slip off the back, right? And the other way that we could look at this is you can imagine that the cart is traveling to the left. So it's going to the left, and the driver slams on the brake, and that means it'll have negative acceleration, so the acceleration vector's to the right. And in this case also, we're worried about the block slipping off to the left. So in both these cases, we don't care about the velocity. What we care about is the acceleration. Now, the other part of this diagram is that the one force on the block is the tension force of the cart trying to pull the block along. And we don't show the frictional force because it's the link between the block and the cart. Now, to calculate this link, it's the mu, which is the coefficient of friction between the block and the cart, times the normal force of the block. And that's the amount of friction there is. And the tension force we can calculate from the back of the train. So this is whatever the acceleration is times the mass of the block. That's how much force it takes to accelerate the block. And if the tension force is greater than the frictional force, then the block will slip. If not, the block won't. And that's the whole way you solve this problem. And I encourage you to come back and look at this example problem. And now we move to the next scenario, the pulley scenario. This scenario is also a two-body problem, where the link between the two masses is the string around the pulley. And often on the problems, they'll say the mass of the string and the friction of the pulley is negligible, so we don't have to worry about that at all. The key to being able to understand how to analyze the pulley problems is that we get to orient the XY plane for each mass independently. So we look at the pulley and we see which mass is heavier. So let's say M2 is heavier. So that means M2 is going to drop and M1 is going to go upward. So we orient the XY plane so that the positive X is going down for M2 and the positive X is going up for M1. And if you do this, the equations work out fine. So we look down at calculate the acceleration for this system, this two-body system, and we have the positive gravitational force for M2, because that's the positive direction, the positive x direction, and the negative gravitational force for M1, because that's the negative x direction. And that equals the masses together times the acceleration. Now to get the tension force, you start from the front of the train, that would be M2, or the back of the train, M1, and from the back, then it would be the gravitational force of M1 plus what it takes to be able to move M1 at that acceleration. So that's about all we need to know for a pulley scenario, and if you analyze it in this way, you can answer any question. And I encourage you to come back and look at this example problem. The next type of pulley scenario is called the Atwood pulley, and again, the key here is that you orient the XY plane so that it is in the direction that we anticipate the the masses will move, and you can see it, how it's done there. And the only force that's going to make this move is the gravitational force of M2. M1 is sitting up on a table, and it's just being held back by friction, and you calculate the friction like you normally do from the normal force. And so using that, we see that the equation for the system is the gravitational force of the M2 minus the frictional force in M1. And then that equals the sum of the masses times the acceleration. Now, to get the tension force, we work from the front. The M2 is kind of the front of the train, or from the back. So let's do it from the back. And so the tension force equals the frictional force on M1 plus what it takes to accelerate M1, and that is M1 times A. And with these equations, you can analyze and in any Atwood pulley or similar pulley kind of scenario, and just in this way. And I encourage you to come back and look at this problem. The last set of scenarios have to do with hanging objects. And the first one is where there's a single hanging object hanging from a rope that's not massless, some thick rope. And the kind of question you'll get for this kind of scenario is, where's the most tension? Is the most tension at the top of the rope or at the bottom of the rope? And of course, the answer is at the top, because the rope has weight and adds to the weight, and there's more tension force at the top. So let's skip down to the third one. That you may see something on the exam like this, where there's an object hanging from a spring. And the key thing to know about this is that the distance that the spring stretches is proportional to how much weight is hanging from it. And it's according to this little equation. And in that equation is the spring constant. And the spring constant for a very stiff spring would be high, and for a weak spring would be low. So there may be a question or two on this. The final one here, the fourth one, is a bar hanging from two ropes. And let's suppose a monkey is hanging on the left side of the bar, then that means there will be more tension on the left rope. And if the monkey's on the right side of the bar, there's more tension on the right rope. And if the monkey's in the middle, the tension is distributed evenly to both ropes. And so there may be a question on that. And now we want to go back up to the second bullet here. It is the object hanging from two strings. And you can see in the diagram to the right that this problem will be described by showing two strings and the theta, the angle between the string and the vertical axis. And this situation is described by these two equations. And the first equation is the weight of the object, that's the gravitational force, is equal to the projection of the tension force on each string onto the y-axis. And so those two have to balance, because there's no acceleration in the vertical direction. And the second equation is the projection of each string onto the x-axis, and those two have to equal each other because there's no acceleration right or left. And using these two equations and plugging in the numbers, you could see in the table on the right, the first table has the two thetas are the same. And if the thetas are small, and that is the strings are closer together, there isn't as much tension than if you spread the strings out and the theta is big, there'll be much more tension. And this is sort of counterintuitive, but this is the way it actually works. The second table shows that if the two thetas are not the same, that the smaller theta, that is the string is more vertical, comparing it to the larger theta, where the string is more spread out, the more tension is on the steep string, on the smaller theta. And this kind of makes sense. So you may get questions on both these, so I encourage you to stare at these tables and really understand what it's saying. So this is the end of the video, where we've gone through all these scenarios you're likely to see on the linear dynamics portion of the AP exam. There are some tips on the central thing to know about each of the scenarios, and I encourage you to go back and look at the problems that were presented with each of the scenarios. So, good luck on the test.